experiment?
Faraday's experiment was, ma'am, I don't remember. The galvanometer.
Okay, look into your
is,
notes. Take the help of your notes. Then try to just paraphrase it. Just try to explain me as if you have with the notes. So at least it will give you a revision, because without that we cannot go further. Okay, take the notebook, open it, and then read it from here. Now then, because you have understood it in the class, so you will be able to recall it. First, tell me the first experiment.
sorry, ma'am,
Yes, your internet is fixed.
ma'am, it's a bit not good. It's fine.
Is it fine? Are you able to hear me, Basmi?
Yes, ma'am.
All right. Yes, we were having a discussion. You take the register, you take the notebook where you have written the notes. You have written the notes in the class. In the class, you must have understood. Now, at least try to just tell me the answers by looking in the notebook. Your video is also closed.
Yes, ma'am. When the magnet, can you see me, ma'am?
Yes.
Can you see me, ma'am? Is my video on?
Your voice is coming very low. Yes. Could you just repeat, Basmi?
Ma'am, can you see me?
Yes, yes, yes. Your voice is also audible. Your camera is also open. Let's just have a discussion kind of thing rather than the question and answer. You take your notebook. In the notebook, you have written everything.
Yes, ma'am.
Just turn the pages, open the page where you've written the Faraday's. First topic was magnetic flux. We did certain numericals. Okay, after that, Faraday's laws of EMI. Before that, experiments were there, right? So, first experiment. Look at the figure. Yes.
When a conductor is placed in the magnetic field, the galvanometer shows a deflection,
Yes.
and this shows that the current exists.
Okay, see,
And
actually, that is not the conductor, that is just a coil. Okay, the conductor is basically in the form of a coil. So, how was the magnetic field created? By using a simple bar magnet. Okay, a bar magnet was brought, which created the magnetic field. Magnetic field led to the increase in the magnetic flux, and that led to current. And how do we know that current was produced? As you rightly said, because galvanometer showed a deflection. That shows the fact that yes, current was existing. Okay, great. Second experiment.
EMF is produced because the coil is moving. So this shows that flux is it's equal to the flux, the rate of change of flux.
Okay, see,
Something like that.
from the second experiment, it's not evident. See, Vasmi, what happens in the second experiment? The coil is allowed to move. Okay, now the coil is moving. But even if the coil comes closer to the the magnet, or it goes away from the magnet, both will lead to the change in the magnetic field. Coil goes near, large amount of magnetic field. Coil goes away, so lesser amount of magnetic field. Okay, so because of that, again the flux was created. There was a change in the flux because magnetic field lines were changing. So galvanometer showed a deflection, showing okay, in that case also you are getting a current. So it is giving you second evidence that yes, current will be existing. Okay. Third one you can leave. Third one was regarding a soft iron coil. Just wait a minute. Yes, ma'am. Are you there?
Yes, ma'am.
Okay. So see, based on this, Faraday gave two laws. What were the laws? Look, you must have written.
Ma'am. Magnetic flux, when the coil changes, the induced EMF will be proportional to the rate of change of magnetic flux.
E is equal to d phi over dt. That is the whole formula. Okay, so see, there was a minus sign, negative sign, and I told you that we'll be doing it in the Lenz law.
Yes,
So
ma'am.
here it is. What is meant by Lenz law is it was observed through Faraday's experiment that if there is a coil, as soon as the magnet was brought or it was removed away, it was observed that the magnetic field is either increasing or decreasing. This
Yes,
was
ma'am.
observed. Increasing magnetic field or decreasing magnetic field led to the increase or decrease in the flux. Yes. So
Yes.
basically, Lenz law, negative sign, negative always means something opposite. Right, something opposite. In the case of axial and equatorial line in the electric field. Do you remember the formula for electric field for the axial and equatorial?
Yes, ma'am.
Try.
Uh,
And if it's wrong, I'll
K
help you.
KQ by R square plus A square the whole raised to 3 by 2.
You, okay, tell me the ideal one, the smaller one. Tell me that.
Um, Smaller one.
2
R
kp by r cube is axial.
by,
Minus kp
yeah.
by r cube is equatorial. Okay. You've recently revised it for the fifth chapter.
Yes,
We did it. We did the same formula in the fifth. Recently, we have done. That's why I asked you. Anyways, see, coming to the flux part that we were discussing, when we had that formula for the equatorial, there also a negative sign was put, right? So negative
yes,
sign
ma'am.
basically told that the direction of the electric field is in the opposite side towards the opposite side of the dipole moment. So here also negative sign is telling you about some opposition only, something is opposite. Now what is it? When the magnetic flux is there or anything is there, we have to determine the direction of induced current. Direction of the means the new current that is there. The direction of this induced current we have to find. So direction of induced current will always oppose. It will be in the opposite direction. It will always oppose the cause that produced it. Because of which this induced current is not because of the battery or your circuits. Induced current in the system is due to some change in the magnetic field, some magnet came, something or the other. So whatever is its cause, whatever be its cause, it will oppose it. That is why you have this negative sign. Let's say the increase in flux caused the induced current and induced EMF. So what will it do? It will make its direction in such a manner that this flux decreases. Whatever is its cause, it will try to oppose that. That is what is meant by Lenz law. This is the Lenz law. The direction of induced current is such that it opposes the cause that produces it. Okay, that is the change in flux. Mostly you will have the change in flux only. The change in flux is causing the induced current. Induced current will try to oppose it only. Whatever produced it, it will oppose it. Its direction will be in such a manner. Lenz law is in accordance with the law of conservation of energy and all. Do one thing, write down the law, this part. I'll give you examples, then you will understand it better. What exactly is this? Okay, write it first, make the heading Lenz law.
Ma'am, I'm done. I'm done.
Okay. See, I'll give you examples and you'll understand what is basically meant by this. Let me give you an example. Let's say there is a coil. Okay. There's a circular coil with the whole apparatus. I'm just drawing this part. Let's say a bar magnet with north polarity is approaching like this. There is a scene. Okay. Now, magnet is coming closer to the coil. Magnetic field will increase or decrease?
Will increase.
Increase. Magnetic field is coming near, the magnetic field lines will be more. So, because of the magnetic field, and there will be flux, and there will be induced current as per the Faraday's law. We had this same experiment only where the galvanometer, which you answered, the galvanometer would show deflection. So, here, what is the cause of induced current? The cause is approaching North Pole. This was basically the whole cause. If this North Pole didn't approach the coil, there wasn't any magnetic field increment, which wouldn't have led to the increase in the magnetic flux and which would never have led to the coming of the induction of the induced current. So the whole cause of everything is this approaching North Pole. Now, current doesn't like this. Whatever is causing it. It's like just think that induced current doesn't want to be existing. Okay. So what will it do? Whoever created it, it will oppose it. Okay. Now, approaching North Pole is the cause. So what will the aim of the induced current be? Induced current's aim will be to repel the North Pole. To repel the North Pole. If the North Pole is repelled away, whole problem is solved. The cause that was the cause that was producing it will oppose. Right? Now see, how can just tell me one thing, Vasmi, how can the North Pole be repelled?
We have to put another North Pole.
Exactly, very good. One more North Pole. It means if this coil somehow this develops a north polarity, the North Pole will be repelled away. Now, coming to the direction of induced current, ultimately we are seeing what's the direction of induced current. That is our task. Task to see direction of induced current. This is basically what is our task. For that, we are doing all this story part. Now, I told you to check the direction of current using the polarity. Just put an arrow and write the same arrows here. You see, this is giving anti-clockwise. So, direction of current will be anti-clockwise. Reason I have told you, this you have to write. And basically the question will be what's the direction of the induced current? So direction of the induced current will be anti-clockwise in this case. Got it?
Yes, ma'am.
So this is what is Lenz's law, that the induced current's direction will be in such a manner that it opposes the cause that produces it. If it is coming, okay, it will repel. Let me give you one more example. Let's say this is a coil When I just draw this part, I hope you get galvanometer and all are connected. I'm just referring
Yes,
to.
ma'am.
Okay. Let's say this is South Pole, North Pole. South Pole is coming. So see, what is the cause of the current approaching South Pole?
Yes, ma'am.
So what will the aim of induced current be?
To have a
To
south, uh, yeah, south polarity.
what will be the aim? What
Um,
will it try to do?
to produce a south polarity.
To repel South polarity. To repel the South Pole. Okay. Cause is this. Aim means you're just opposing it.
Mm.
Okay. So see, if this develops a South polarity, so look, this is clockwise. So clockwise is the direction. One more example, let me give you. This is the coil. This is the bar magnet. Let's say this is moving away with some velocity. This is moving. So yes, moving away. Will the magnetic field increase or decrease? It will.
Will decrease.
It will decrease. See, magnetic field decreases, so flux will
Decrease.
decrease. So this means their flux is decreasing. There's a change in flux. You are not concerned with whether it's increasing or decreasing. You are concerned with whether it's changing or not. Change. Now, change can be anything. Change can be a good change, a bad change. Bad change in the sense a decrement or an increment here. But here, this is not related to that. Here, it will be just the flux change. Change in the flux means induced current will be reduced. And induced current will be produced. Now, see, what was the cause of all this induced current?
The magnet moving away.
Yes, the magnet moving away. Okay, the going away of North Pole created everything. If this wasn't going away, the magnetic field wouldn't have changed, the flux wouldn't have decreased. Like this is just think it like a person, a frustrated person who doesn't want any change. So think it like that. Okay. So see, coming to the aim. What will the aim be now?
To bring it back.
Bring it back means to attract the North
Uh,
Pole.
to
This way
attract
only the work will be disrupted. So to attract the North Pole. Now North polarity can only be attracted by
south polarity.
South polarity. So this will develop South polarity that will again lead to direction. Which is what is the direction here?
Clockwise.
Clockwise. So this scenario with this answer, but a lot of explanation. And do mention these things also. That why do you think that this is the cause? This causes because of this change, right? If one last example I give you here, there are lots of questions based on Lenz law, like these only. It won't take time. It will not take time, but it's just that if you have understood the concept well, you'll be able to answer. Or if there is a very famous question, a ring is there and a bar magnet is dropping to it, that I'll give you in the assignment.
Yeah.
So this is the coil. Here, let's say this time the south polarity is moving away. See, as soon as you have the south polarity moving away, magnetic field decreases, the flux decreases. This is a change in the flux. So when we are talking about change in flux, this will lead to induced current. Yes. So now we have to determine its direction. No right hand, left hand rule. All this started because of The moving away
South Pole.
of south. Yes. Now tell me the aim.
To attract the South Pole.
Very good. Aim will be to attract the south polarity. Okay. To attract the south polarity. How can south be attracted?
South polarity should be put in the coil.
Which polarity?
North.
North. Yes. North is there. Put the arrows. Make the arrows. So this is anti-clockwise. This is what is your Lenz law. Lots of cases we have seen. Have you understood this?
Yes, ma'am.
Please write it. If there's any doubt, please ask. Okay.
Yes, ma'am. Can you scroll down? Can you scroll down? Ma'am, can you scroll down? I'm done, ma'am.
Okay, see, Basli, there's this concept is there in class 11, not class 11, sorry, in your NCRT. Okay, in NCRT, this question is given. So I'm doing it in the form of an example. All these questions, one or two, are there in your NCRT. The rest I've done. But this is from your NCRT only. So you will find this in your back exercises. Okay, back size. It is.
Ma'am.
Okay, see, it says that let's say this is a coil. Okay, this is a coil and this is gaining entry into the uh, field of magnetic field. These are all the magnetic field lines from. And cross shows, is it inwards or outwards?
Crosses outward.
No. Cross shows it's
Mhm.
inwards. Cross is inwards, dot is outwards. Okay.
Okay, ma'am.
Now see, the coil is coming inside. Now tell me what will happen to the magnetic field. Will it increase or decrease?
Will increase.
Magnetic field will increase. Okay. What will happen to the flux? Will it increase or decrease?
Increase.
It will decrease.
No, increase.
Increase. Flux increases. So what is the task of what's the aim of the induced current?
Uh, to move away.
To
Induced current. Ma'am, induced current will be produced, right? The magnet should move away.
this is the cause. There's a change in the flux. This will lead to an induced current.
Will
So what have we studied before? What is the cause here?
the cause is to the approaching. What is it called? It's a north pole. No,
Where
but
do you see
poles
a
are not
magnet here? Is there any induced current here or not?
there. Is
So why is
there is
it? How can we say there is an induced current? What's the cause?
there's a
Why
magnetic field.
magnetic field? If you don't have the magnet, why are you getting confused with the above example? That example is separate, this example is separate. Whatever you are able to observe, you answer. Must me try to answer with your full command, whatever you're trying to answer with all the whichever makes sense. Okay, because in the exam you will not have these fixed questions. Any question can
Hmm.
come. We just now said that you only told me that magnetic field increased, flux increased, because of which we have induced current. I'm asking you the same thing. What's the cause? Cause is the increase in the magnetic
Magnetic field.
field in the flux. That is causing. Okay, whatever you've studied, just apply. It's not necessary
Okay,
there
ma'am.
has to be a magnet. Magnet is not there because magnetic field is there already. Okay. Now you tell
Okay,
me,
ma'am.
what will this induced current try to do?
It will try to increase the magnetic field.
Why?
No, it will try to reduce the magnetic field.
It will try to reduce the magnetic field. Don't just say anything that is written on the screen. You have told me the answers correctly before this. Just answer this one also correctly, okay? Magnetic
So,
field, induced current will try to decrease it. Increasing magnetic field caused it. So it will decrease the magnetic field, okay? Just stay on your concept. You know it well. You've answered the previous concepts very well. So you know this, okay? Don't be confused with what is written or what is not written. So magnetic field has to be decreased. Now, these fields are what? If you look here, these magnetic fields, the original magnetic fields are inside the page.
yes,
Now, there is an induced magnetic field, this one, that will come because of the current. This induced, there will be one more magnetic field. Okay. Now, see, there are two possibilities. One is that this magnetic field induced can be like this, means coming out of the page, or it is pointing inwards. Both are possible, right? Now, see, if this is the induced, how will I get the net magnetic field?
will cancel each other out.
Not cancel, subtract. Cancel when you know the magnitude is the same.
They're equal.
Two vectors in
It will,
opposite direction, subtract. Yes. Cancel only in that case when the magnetic field's magnitude is same. Okay. Now coming to this, if suppose this is the direction, will it increase or decrease?
it will increase.
It will increase because they will get added. This case will be subtracted. So which one should we prefer, the first one or the second one?
The first one.
Why?
Because it will decrease the magnetic field.
Very good. This is how you have to answer. Okay, whatever is written, you ignore it. Whatever is your concept, you're going to apply that. Yes, here the magnetic field is getting decreased. Magnetic field was already increased, which was producing the current. If we add it again, this will further increase. No, we cannot add. The induced magnetic field, the new magnetic field that we are talking about, the induced one, that has to be outwards. Now see, Vasmi, one is inwards, this induced one is outwards. This is the induced one and this is the original one. Yes, this is the
Yes,
case which we have chosen. See, direction of induced current. You take the thumb along the magnetic field, curvature of finger will give you the direction of current. Okay, where is the induced magnetic field? Outwards, that's what we have decided. So thumb also I have
yes,
taken. Where is the curvature of the finger going? It is going, this will be anti-clockwise, right? Okay, this
yes,
is
ma'am.
anti-clockwise, no? So it means the direction of the magnetic field, the induced current's direction will be this. Now you've got it?
Yes, ma'am.
Okay, it's one more question. Let's say here is a coil. Okay, this is coming out of it. This is the second one. Okay, this is coming out of it. Now you tell me what all things are happening.
Magnetic field increases.
Magnetic field? Yes, what happens to magnetic field?
Increases. It
It,
increases.
why?
So there's a flux increase.
Why
Uh,
is magnetic
that
field
reduce
increasing?
one because it comes. There is a current.
Huh? What? I said
Um,
a coil is moving, this coil is moving out of here. So what is happening to the magnetic field? Is it increasing or decreasing?
it's moving out. So no, coil is moving out, so the magnetic field will decrease. So
Yes.
the flux will decrease.
Yes. Now you got it? Why you were wrong in the first
Yes,
place?
ma'am.
Here in the first case, the coil was entering. Okay. So when the coil enters, lots of magnetic fields are coming. It is going inside.
Mm.
Now, this was already there. This is leaving. This is exiting. So when this coil is exiting it, so what will happen? Magnetic field will be there. Magnetic field will be decreasing because lesser of magnetic field lines are going. See, this part has no magnetic field and slowly it is leaving. And you are right, magnetic flux will also decrease. This whole change will cause the induced current. Now, this is the cause. What is the aim of induced current now?
Aim of induced current is to increase the magnetic field.
Exactly, to increase the magnetic field. One magnetic field is already inwards. If the induced is also inwards, then only the net magnetic field will be
Yes,
given by the
ma'am.
addition. So see, if this magnetic field induced is also inwards, means thumb inwards,
Mm.
what is this
Uh,
direction? Anti-clockwise.
Clockwise. Sorry,
And
anti-clockwise.
anti-clockwise, okay. So this will be the direction of the induced current. Okay, I am naming this as the first one and this as the second one. Now see, the explanations are already written here. This explanation is for the first one. Induced current will try to increase the flux because magnetic field is decreasing. So direction of induced current is in such a way to increase the magnetic field. The rest of it you already know. For the first, for this one, which we discussed, the second one. Induced current will try to decrease the flux. Magnetic field induced will point outwards. So direction of induced current will be anti. Okay. Now Lenz law
Ma'am.
is completely clear because this overs with the Lenz law. Okay, now I think you have understood also by the examples and all. Okay, just be attentive because here the problem is that if one of the points is wrong, the entire answer becomes wrong. Okay, so I'll give you assignment also based on this. We'll practice. First write this properly. Okay.
Yes, ma'am. Ma'am, can you scroll down? Done, ma'am.
Okay, look, now the next topic is motional EMF. Now, what is this? EMF we have studied, voltage. Okay, now if your conductor is moving, motional means it is related to movement, motion, right? So, motional EMF means the EMF that is occurring in the body when the conductor is moving. Okay. So, see, definition says this EMF induced across the ends of a conductor due to its motion in a magnetic field is called as motional EMF. Like, see, very easy topic it is. Let's say we have this exact same derivation as there in this is from her NCERT, so draw it as it is in the exam also. Okay, this is
So,
from
ma'am.
the NCERT. So, these are certain conductor like the tracks, okay, on which here you have the conductor present. These are just like acting as tracks where we can move this conductor. Okay, when we are moving this conductor, so then it will give us the EMF. Motional EMF can only be possible then. L is the length of this conductor, and this is moving with a velocity of v. And let's say this distance is x, which will be changing. And
Yes.
magnetic, these blue lines, these are magnetic fields that are pointing inwards. Got it?
Yes, ma'am.
Okay. See, here if I write about the magnetic flux, if I want to write about the magnetic flux, so what is the formula of the flux?
Flux is BA
B dot
cos theta. Yeah, B dot.
right. If I say flux is BA, now from here, this is a rectangle that can be clearly seen. If you look at this part, this X, this L. What will be the area of a
Area will
rectangle?
be X into
Yes,
X
yes,
into L.
correct. X into L. So I can say from here, flux is equal to B into X into L.
Mm.
This is the magnetic flux. Now see, EMF is equal to minus d phi over dt.
Yes, ma'am.
I can say minus if I differentiate this. I put BXL over dt.
Mm.
Okay. If I write here minus magnetic field out, the length of the conductor is fixed. I am left with dx over dt. Yes, Basmi, tell me, what is dx over dt?
Velocity.
Velocity. Yes. So this is the speed. So we finally get the formula of motional EMF as minus BL. Now minus sign you completely have understood through the Lenz law. This is the same minus sign. So what is E? E is the motional EMF. B is the magnetic field. L is the length of the conductor, and V is the velocity of the conductor. Okay.
Yes, ma'am.
Directly you can use when you have to put in the values. You can use this as this formula directly. You can use E is equal to BLB for the potential only, like the EMF. Okay. I'll tell you a few more things. First, write down this, and this is a derivation. Okay, this is a small derivation. Please write this.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, I'm done. And
Okay, see, coming to current, force, and power, these are three formula that we have, which we already know. Now, this is the general formula of EMF that we put. The current is equal to E by R. So, when you have the new formula for the EMF, you can put it if the current is asked. You see, this will be current will be equal to BLV divided by R. You can use this. Some of the questions are there that have come. This is not mentioned separately, but see, E is equal to BLV. You put E's value as BLV, you will get the answer. Okay. Talking about force, force is equal to PIL. Now, see these formula you only have to apply when you have the motional EMF present. Okay, conductor is also moving. The motional EMF term is mentioned, so you'll get a hint that this is referring to this section. Otherwise, you use this old formula only. Now, F is equal to BIL. We discussed its derivation and all. Just look back. So force is equal to B into now current. Current is what? BLV by R into length. See, BIL. So we can say this is B square L square V by R. Okay. And one more thing, power also has been asked. These are just three things that I found are coming in the exams repeatedly. Power is also there. Power is important. Power was asked once. This is force into velocity. The force is B square L square V by R. This is V into V. That makes it B square L square V square by R. Okay, so few formula if we write, R here is the resistance. BLV we know, current, I is the current. F is the force, yes, on a straight conductor. While P is the power. Okay, write down this page. Then we practice numericals. Okay, let's look at this question. This is the question from your NCRT. It says, it's a very easy question. See, it says an aircraft with a wingspan of 40 meter. Wingspan is there like this. This is 40 meter. Okay. Then it says with a speed of moving with a speed of 1080 kilometer per hour in the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the magnetic field, so vertical component we discussed in Earth magnetism, this is 1.75 into 10 to the power minus 5. Find the EMF that develops between the tips of the wing. EMF we have to calculate. See, EMF, this is the length given, this is the velocity, this is the magnetic field. But before anything, speed has to be converted. It's in kilometer per hour, and rest of the things are in the SI form. So 1080 divided by 5 by 18. 1080. This is divisible by 18. This will be 080 by 18. It's 60. All right, so that becomes 300 then. This is divisible by 60. That makes it 60 into 5, which is 300 meter per second. Okay. Now coming to the EMF is equal to BLB. Magnetic field is 1.75 into 10 to the power minus 5. Length is 40, B is 300. Whatever will be the answer. This will be around 13 point something. Yeah, 0.31 will be the exact answer, I think. I'll let you know the answer. This much, something like this will be it. I'll just let you know what's the answer. Okay. You write it meanwhile.
And can you scroll down?
There is 0.21, okay, not 31.
Okay, ma'am. I'm done, ma'am.
Okay, the last topic for today. See, this topic isn't there in your means this is there in your NCRT, but now this has been deleted from your board exams. Okay, so don't prepare it, don't learn it. I'll not be giving you any assignments based on that. It's just that you should just be aware, just in case if you witness a term anywhere, so you shouldn't be confused. What are these? When you have certain sheets or blocks are there or sheets are there, some amount of current is there that flows in a spiral format like this. This is known as whirlpool. So eddy currents are basically known as the Foucault currents or the whirlpool currents. So whenever you have seen blocks or sheets because of the change in the magnetic flux, there will be EMF induced, and this EMF induced, or you can say the current that flows in the form of these blocks, like spirals. Okay, these are basically spirals which are known as the whirlpool. See, there are many applications of these. These are used in induction furnace, electromagnetic damping, the electric brakes, and the speedometers of the cars. Okay, there these the eddy currents have a lot of application. But again, I'm saying this has been deleted. Nobody will ask you anything in your regular CBSE exam. Just make a note point, write it, and write this is not there in CBSE just for your knowledge. That's why I've written it also very concise. Earlier there were few classes on eddy currents and the questions also used to come. Now nothing will come. Just have this so that if you just witness the term, you are able to identify it. Okay.
Okay, ma'am. Can you scroll down? I'm done, ma'am.
Okay. See, now just one topic is left from this, that is induction. Okay. Induction is
Okay,
basically
ma'am.
the preparation of whatever you've studied. One last topic is induction. Two kinds of inductions are there, self-induction and mutual induction. Now, what is the meaning of this induction and all will be clear only when you are thorough with what we have done till now. So, tomorrow is Saturday, Sunday. In these 2 days, will you be able to study these two topics at least?